Hello everyone, welcome back to deterministic optimization. We have our last lesson in this module on further development of simplex method. We'll put everything together and to see a concrete example of solving an LP using simplex method. So here the learning objective is to familiarize yourself with simplex method to actually solve an LP. And we'll carry out one iteration in detail of a simplex method. And you are expected to be able to carry out this simplex method on this problem till it terminates. Okay, so here's a problem set up. We have a linear program given in the blue box. And it's maximization problem first. Okay, it maximizes 2x1 plus 3x2, subject to all these 5 inequalities. So apparently this is not a standard form LP, right? How do we solve this? Well, in order to solve this by simplex method, we need to turn this into a standard form LP. I think everyone can do that at this point. And to help us visualize what simplex method does geometrically, we're going to also plot the feasible region for this original LP first. So because there are only 2 variables in this case, we can easily plot it on a plane. So here is the plot. This is x1 variable, this is y-axis is x2. And there are 3 inequalities here and plus 2 non-negativity constraints. So in fact, in total there are 5 inequalities. And if you look at the signs of the inequalities correctly, then the feasible region of this LP is this P here. Okay, so that is the feasible region of LP in the original form. And you can also see that all the blue points here are extreme points, right? These are extreme points. The green points here are basic solutions, meaning they have 2 at each one of them. There are 2 linearly independent active constraints, but these green points are not feasible. So they are basic solutions, but not basic feasible solutions, whereas the blue points are basic feasible solutions. But this is in the original space, x1, x2 space. When we transform this into standard form LP, this is the standard form LP. And we all know that first we need to turn the max into mean problem. And then we need to add slack variables, right? Here, because it's less than or equal to signs here, we're going to add x3, x4, x5, right, to these 3 constraints to make it equality. And x3, x4, x5 are non-negative, and x2, x1 are already non-negative. So now I have a standard form LP and can start simplex method on it. And also notice that the right-hand side here are non-negative, right? So this B here is a non-negative vector. That makes us our life easier because I can easily point out a basis, a basic and a basic feasible solution to the standard form LP. How? I can just choose this x3, x4, x5, right? These 3 columns as the basis matrix. And this is identity matrix, so it has to be invertible. So this has to be a basis matrix. And the corresponding basic solution is 10, 60, 60 for x3, x4, x5, and 0, 0 for x1, x2. And it satisfies all the constraints because it satisfies equality constraints and it satisfies all the non-negativity constraints. So that is a basic feasible solution and an easy one to find. All right. So use that, we can start simplex method. And I want you to pay attention to link this standard form LP back to the original LP. So this standard form LP is in 5 dimensions, right? But the first two dimensions correspond to the original variables, right? So this basic feasible solution we just found, 0, 0, 6, 10, 60, 60, has the first x1, x2 being 0. So that means it's actually correspond to this point, origin, in the original LP. It's right here. So we start from a basic feasible solution corresponding to this point. And I want you to pay attention later when you do this, carry out this simplex method to see where next iteration of the simplex method leads us to in this lower dimensional space. Okay. Okay, let's start first iteration. We have already chosen a starting basic feasible solution as we did. Just choose A3, A4, A5, which is identity. And right-hand side is non-negative. So I have found a basic feasible solution, 10, 60, 60, x1, x2 being zeros. And the cost coefficients associated with this basic feasible solutions are the following. The basic part are C3, C4, C5. And they are zeros because these are slack variables. And the non-basic part are -2, -3. So if you go back, -2, -3, 0, 0, 0. So that is our starting point. So next step, compute reduced cost for non-basic variables. We have two non-basic variables, C1, C2. Remember, the reduced cost is computed as C1 minus CB transpose B inverse times A1. Okay, so remember here, C1 is -2, CB is 0. So we don't even need to compute this part. It's 0 here and 0 here. So C1 bar and C2 bar are -2, -3. All right, both are negative. That means the current basic feasible solution is not optimal, and both x1 x2 are candidates to enter the basis. And making them enter the basis means increase their values to some positive value. Let's take x2 to enter the basis. Okay, this is not Bland's rule in this case, but we do not have a degenerate solution anyway. So let's take x2 to enter the basis. You can also take x1. That will correspond to a different trajectory of the simplex method. So given x2 enters the basis, we can compute this direction. Remember, the direction has two parts, the basic part and the non-basic part. The non-basic part is quite easy because we're going to keep x1 at 0 and only increase x2. So the non-basic part is 0, 1. Okay? And the basic part is given by this formula, -b inverse A2. And remember, B is identity. So in this case, it's just -A2. What is A2? Well, A2 is this column here, right? 1, 2, 3. And negative of that is -1, -2, -3, right? So that means the basic part of the direction has negative components. That means we cannot move along this direction indefinitely. We can only move with a positive finite step size. And to determine that, we need to do mean ratio test, right? And to do mean ratio test, let's look at what is the result moving along that direction, which is x plus theta d, where theta is the step size that we want to decide. X is the current basic feasible solution. So x, B1, B2, B3, these are the three components of the basic variables, which are x3, x4, x5. Right? Remember, B1 is the first column of the basis matrix, which is B3, which is the third column, right? Which corresponds to x3. So x3 plus theta d3, x4 plus theta d4, x5 plus theta d5 will give us 10, 60, 60 plus theta times -1, theta times -2, theta times -3. So we can see that theta, if theta is too big, these components can become negative, meaning infeasible. So the mean ratio test will be over the d's that are negative, right? So is the xbi divided by the negative of dbi for the dbi that's negative. So the negative of that is positive, right? So we get the mean ratio of 10 divided by 1, right? 10 divided by 1 here, 60 divided by 2, 60 divided by 3. That gives 10, 20, 30, and 20. So the minimum ratio is 10. And this is unique. So that means the first basic variable is going to become 0, become non-basic. So that is x3. So x3, x is the basis. So let's look at what is the new basic variable feasible solution. Well, the new basis is A4, A2, A4, and A5. Why? Because remember, when we compute the reduced costs, we decide to pivot on x2. So make x2 from non-basic to basic. So A2 enters the basis, and x3, x is the basis. So the basis becomes A2, A4, and A5. And then we can compute the new basic variables, x2, x4, and x5. How to compute that? Well, you can just do here, right? Because we have computed theta to be 10. So if theta is 10, this becomes 0. So x3 becomes non-basic. And x4 becomes 60 minus 20, which is 40. And x5 becomes 60 minus 30, which is 30. Remember, what is x2? Well, x2 goes from 0 plus theta times 1, right? d2 is 1. So x2 becomes 10 because theta is 10. So that's why the new basic variables are 10, 40, and 30. That's the new basic variables. And the non-basic variables are, of course, 0 and 0. So this is a new basic feasible solution. And then we can start simplex method again on this basic feasible solution, compute reduced cost, find the one with the negative reduced cost to enter basis, and compute direction, and do mean ratio test, and so on. So I want to bring your attention to what is x1, x2 here. Well, x1, x2 is 10, 0. 0, 10. So if we go back to the original graph, we started from 0, 0, remember, right? And now we're at 0, 10. So in one iteration of simplex method, we have moved from this initial basic feasible solution to this new basic feasible solution. And you can, in this simple case, you can actually directly figure out what is the optimal solution. We're minimizing 2x1 plus 3x2. So the optimal solution, I think, is going to be probably here. So, well, maybe here. So it's 60 here, and this is 48 plus. Well, this two probably give you both optimal solutions, I hope. So we are one step closer to the optimal solution by one iteration. Okay. So yes, so that is one iteration of simplex method. And let's summarize. We have gone through a detailed steps of simplex method here. You should be able to carry out this remaining iterations until the simplex method terminates. And in this case, we see that the simplex, this optimal solution has to be bounded. So the simplex method will terminate with the finite number of steps, actually only 2 more iterations, and you should be able to find the optimal solution. So that is a detailed example of simplex method, and this concludes our discussion on simplex method for this part of the linear program. Thank you very much.